Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome to this course on gas turbines and jet engines. So, today is lecture 15 of this course. So, this is the final lecture or final class of week 3 and in this class we are going to compare the performance of all the different gas turbine cycles that we have studied till now. We have studied 8 cycles till now. So, we are going to compare all the cycles in terms of their efficiency variation with R and T and net work output variation with R and T. Okay. Apart from this, we will also introduce the concept of design point calculation and we will discuss and learn how to create performance characteristic maps from this design point calculations. Okay. So, this class will in this class we will finish this first part which was on the ideal gas turbines, and from the next class onward we will go into details of modifications needed in terms of analysis for actual gas turbine cycles or actual gas turbines. Okay. So, as I said, the main concepts which will be covered are twofold. One is that design, what is design point calculation? We are already doing design point calculations without defining this term. Okay. So, we will define that, and how to generate performance maps or performance characteristic maps and then compare. Okay, so, this and then compare all the different ideal gas turbine cycles, 8 cycles till now we have studied, and that is like that covers all the cycles. So, simple Brayton cycle, Brayton cycle with regeneration, Brayton cycle with reheat, and Brayton cycle with regeneration plus reheat, and then all these 4 cycles with also intercooling added. Okay. So, total 8 cycles. So, we will see their performance characteristic and compare them to each other. So, what is a design point calculation? So, till now we have solved various problems. For each of the cycle we have solved one problem where we have specified what are the values of the design parameters. Okay. What are design parameters? Design parameters are parameters which are used for designing a gas turbine. So, these are the initial parameters which are need to be defined. So, for gas turbines, for ideal gas turbines, the design parameters are this R which we already know, the overall pressure ratio, and T which is the temperature ratio. In it can also be represented in terms of the turbine inlet temperature. So, turbine inlet temperature is the actual design parameter which is the maximum temperature possible, but for given ambient conditions maximum temperature possible will be same, not same, means it is represented directly by this variable T, temperature ratio. Okay. So, for a given set of values, let us say that R equal to 10 like we had taken and T equal to 5, that was the case for our problems. We evaluate the performance parameters. Okay. Numerically we evaluate the performance parameter, in our case efficiency and net specific work output in non-dimensional form or dimensional form, it is up to us. So, we have done this in dimensional form, but it can be easily non-dimensionalized by dividing it with Cp into T1. Okay. So, from the design parameter, let us say that if we are thinking in terms of efficiency, so for a given value of R and T, let us say this is the value of R and T is fixed. So, this at this point let us say T is 5. We obtain what is the efficiency. Okay. So, this efficiency is let us say some value like we will see later 0.48 we had obtained for the simple Brayton cycle. So, we plot this point and then redo the calculation again by taking a slightly different value of r. Okay. So, each of this calculation is done for a fixed design value or fixed design point, fixed design parameter value or fixed design point, and thus is called as design point calculation. Okay. So, one calculation like this is a design point calculation. We will come back to this, but let us see an example. This is one of the problems that we have solved. This was the second problem on regeneration. So, here also we had the same parameters 300 and 1500 Kelvin temperature range. So, T equal to 5 and R equal to 10. So, for this design point which has value of R equal to 10 and T equal to 5, we obtained what is the efficiency. It was found to be equal to 61.4%, and we obtained what is the net specific work output, which was 446.08. We could have non-dimensionalized this also by using CPT1. Okay. So, in that case, so Cp into T1 will be of the order of 300. So, you will get some value around 1.4, 1.5. Okay. So, this is an example of a design point calculation. So, we have done these calculations for different cycles, but when you consider a single cycle, like say for this regeneration cycle, we do a design point calculation, we find the values and then we take a slightly different value of one of the parameters. In this case, generally it is T is kept fixed and R is taken as another value. Let us say R equal to 11. Again the same calculations are done. Okay, it is done computationally, it can be done in iterative fashion directly, and we obtain again the corresponding value of efficiency and net work output. Okay. So, each design point calculation gives us one value for the performance parameter efficiency and one for the net work output. So, like this if we keep on continuing, okay, let us say for the simple Brayton cycle, and this is R equal to 1. So, at R equal to 10 we have some value, at R equal to 11 we get another value of efficiency, R equal to 12 we get another value. Like this if we keep on doing, we get a variation of how efficiency changes with R. Okay. So, we could have directly plotted in for the ideal cases, but when we go to real cycle there are no direct expressions which can be obtained, then we have to do design point calculations like this and then plot the performance parameters. Okay. So, like this you get for. So, here there is no dependence on T, but if it was dependence regeneration cycle, we have both T as well as R dependence. So, we find that for T equal to 5 we get this value, for R equal to 10, then R equal to 11, R equal to 12 like this, and then we join the lines to get a performance curve. Similar thing we can perform for T equal to 6, again starting with R equal to 10, 11. Need not start with R equal to 10, we can start from R equal to 2 also and keep on performing, and we draw another curve, and like this if we keep on generating curves we will get the full performance map in terms of efficiency variation versus R and T and net work output versus R and T. Okay. So, this is the way performance maps are generated, and this is particularly useful when we go to real cycles where this closed form expressions cannot be obtained for this efficiency and work output. Okay. So, by changing the values of design parameters, new values of the characteristic parameters efficiency and W net are obtained, and by repeating the process over a range of R and T, we get the performance characteristic maps generated. So, this is this can be means implemented as a computer program, and then this entire process can be repeated by using loops, and you can directly generate the performance map. Okay. Now, we will do a comparison before we move on to the next topic, because we have gone through all the different cycles. We will do a comparison of the output or performance of all these 8 cycles, okay, how they compare with each other. So, which one is suitable, for example, which has the highest efficiency at a particular value of R, at a different value of R and T, which has the higher efficiency or highest efficiency which has the highest work output at different value of R, all these things we will see. Okay. So, for one single design point we had done calculations by hand as illustrative examples in our cases, and we have obtained this table which we had discussed in the previous class. So, we have seen how the efficiency is different for each of the cycle, going from a minimum value of 40.4 for intercooling plus reheat cycle to a maximum efficiency of 72.2 for the combined intercooled reheat and regeneration cycle. Okay. So, remember that these points are all for separate gas turbines. So, for a single gas turbine, when we do design point calculation, we will not be varying the actual cycle, but we will vary the value of R and value of T. Okay. So, this is a very complex complicated image. Okay. So, let me explain it in with some time. So, what I have done is we have plotted the efficiency variation with R and T for all the 8 cycles on a single graph. So, that everything can be quantitatively compared. Of course, this has made the entire diagram very complicated, but if we go step by step through explanation, it can be clear that what type of differences we see. Okay. So, let us start with the simple Brayton cycle. Simple Brayton cycle is shown by this black line, okay, by this black line. So, we will use a color which is not used at all, so as to distinguish between all other colors. Okay. So, this is the simple Brayton cycle line. We know that the efficiency keeps on increasing, and if you consider a particular value, let us say very high R value of 25, we see that the efficiency will be around 60%. Okay. Similarly, for our problem we had a value of 10, okay, and temperature ratio does not matter. So, we are at a value of 10, we were at this location, okay, which is slightly below 50. So, we had obtained 48% in our case, okay, which we see also that the graph also agrees with us. Okay, this is for simple Brayton. Now, all the solid lines of different colors. So, we have specified each of the processes by different colors. The solid lines are for processes without intercooling, and the corresponding same color dashed lines are for processes, same processes, but now with intercooling also added. Okay. So, we will go to the next one that we have studied, which is regeneration. So, regeneration is shown here by these red lines, okay, solid red lines. So, T equal to 2, T equal to 3, like this, T equal to 4, T equal to 5, T equal to 6 up to this point. So, you can see that regeneration, as we had discussed qualitatively, quantitatively also we can see how it decreases, and then there is a crossover point with the simple Brayton cycle. For a very low value of temperature ratio T equal to 2, which is not practical, we get a very quick crossover at a very less value of R, but for more realistic values, say T equal to 4, okay, the crossover occurs after significant at a significantly higher value of R. So, in this case it is around 12, okay. At T equal to 5 the crossover is even higher, it is around 17, and you can calculate what is the value. T equal to 6, it goes to much higher value, okay, around 23. So, like this. So, each of these red line shows the variation of efficiency, and you can see how the efficiency decreases. So, at R equal to 1, right, this is the R equal to 1 point. All the non-regenerative curves have efficiency equal to 0 at R equal to 1. All the graphs with regeneration included, like all the systems with regeneration included, at this point they have the value equal to 1 minus 1 by T, okay. Efficiency is equal to 1 minus 1 by T. So, for example, T equal to 5, the value will be equal to 0.8, 1 minus 1 by 5, so 0.8. T equal to 4, it is 0.75, T equal to 3, it is 0.667, T equal to 2, it is 0.5, T equal to 6, it is 0.833. okay, 1 minus 1 by 6, and our curves agree with this theoretical value. Okay. Now, the third process that we had studied was for reheating. Okay. Reheating, we found that the characteristics are very different from regeneration. It is similar to that of simple Brayton, but without but at a we get a lower value of efficiency. Okay. So, reheating here is shown by these green lines, okay, although it is very crowded at this point. I will try to explain quickly. Okay. So, for example, this line t equal to, this is corresponding to reheating at t equal to 6, very near to it is t equal to 5, t equal to 4, like this, and t equal to 3, t equal to 2 is very small, less, but that is not practical. So, this is t equal to 3. So, at a very narrow range you get all the variations of the reheat, and we see that the efficiency increases with t. So, for example, at a very high R value of 30, the efficiency is of the order of 0.44, 44% only for t equal to 3, and for t equal to 6 it goes to a value of slightly above 50%. So, maybe around 54, 55%. Okay. So, our case was t equal to 5 and R equal to 10, we can find out what value we get from the performance maps. So, these are the characteristic maps. Okay. So, this can directly be used to get the value of efficiency, and similar map can be used for work output instead of doing those or solving again the problem corresponding to each of the design values. Okay. So, for this reheating case, for t equal to 5, we were somewhere around here, for R equal to 10. So, this is just above 40%. So, we had obtained a value of 41% in our case, 41.9%. So, this is slightly above the 40% line. Okay. So, around 42%, and that is what we got. And for regeneration, for t equal to 5, we were at this point R equal to 10, t equal to 5, this is slightly beyond the 60% mark. So, it was 61.4%, okay, and again our graph agrees. So, similarly, without solving we can now say that at R equal to 15 for t equal to 5, we will have a value which is around say 56-57% for the regeneration cycle. Okay. It is decreasing and we will get a value of 56-57%. So, similarly, you can say what will be the value for reheat. So, it seems that it will be around 46%. Okay. We can calculate and verify. Now, with intercooling, so before going to intercooling, we also had the combined regeneration and reheat cycle. Okay. Now, we noted that adding regeneration to normal Brayton cycle decreases the efficiency, but adding regeneration to adding reheat to normal Brayton cycle decreases the efficiency, but adding reheat to regeneration increases the efficiency. Okay. So, these are shown here by the solid blue lines. Okay. So, this is for t equal to 2, similarly for t equal to 3, t equal to 4 and t equal to 5, t equal to 6. You can see that the efficiency is much higher as compared to the corresponding value for regeneration. So, for example, for t equal to 5, the solid blue line gives us a value of around say 66%, which is considerably higher than that of this red line, which is the only regeneration process, which is 61, around 61%, and that is what we had obtained also 66.8% and 61.4%, right. So, similarly, we can see that this also decreases quite slowly. So, even at R equal to 25, which is a very large value, the efficiency at t equal to 4 is still very near to 60%, around 59%, very near to 60%. Okay. So, we can directly get the values, and you can compare what percentage increase is there by adding reheating quantitatively from this graph. So, these are all the 4 cycles without intercooling. So, now similarly, we have all the cycles with intercooling also, with corresponding colors as the non intercooled cycles, but with dashed lines. Okay. So, I will just quickly summarize this part, because otherwise it will get repetitive and very complicated. So, we know that, so for example, these dashed lines in green are the case for reheat plus regeneration. So, we see that for t equal to 3, okay, comparing all the cycles without regeneration, we get the lowest efficiency for this combined reheat plus reheating plus intercooling cycle. That is true for any other temperature ratio also. For t equal to 5 also that is the case, for even for t equal to 6 also you get the lowest efficiency. Okay. Now, we have some lower efficiencies here, but those are for cases with regeneration where the efficiency keeps on decreasing below the, so this is after the crossover point. So, we will not be operating the cycle there. So, for our case say r equal to 10, t equal to 5, we were somewhere around here. So, just around 40% okay, was the efficiency, slightly above 40%, which is the lowest efficiency at r equal to 10 for all the cycles. Okay, I think that is what we obtained, just above 40%. Now, pure intercooling, when intercooling was added to simple Brayton, we already noted that the effect is less drastic as compared to reheating. So, we get decrease in efficiency. So, for example, this is t equal to 6, this is t equal to 5, t equal to 4. So, efficiency is lower as compared to simple Brayton, but the extent by which it gets lowered is less as compared to that of reheat cycle. So, compared to reheat cycle, in this case the efficiency is still considerably larger, as you can see, around 5 to 8% larger if we compare to pure reheat cycle, okay. 4 to 5% larger probably in these regions. So, in our case also we had seen the same. So, in our case T r was equal to 10, T was equal to 5. So, we were somewhere around this region, okay, which is around 45-46%. What was the value? We had 45%, which was considerably higher by 4 to 4% higher than the corresponding reheat cycle. So, same pattern for intercooling, but higher efficiency than reheat and combined reheat plus intercooling, but lower than the simple Brayton. On the other hand, if we had added intercooling with regeneration, we had noted at the time when we were discussing that here the effect of intercooling is surprisingly strong when it is combined with regeneration, and we get more pronounced increase as compared to adding regeneration to reheating or reheat cycle. Okay. So, this red dashed lines are the intercooled plus regeneration, okay, and you can compare with the solid blue lines which are without intercooling, regeneration and reheat cycle. Okay. So, you can see that for example, t equal to 6, 20 r equal to 20, this is the value without intercooling, but with reheat. Okay. So, regeneration reheat, and the red dashed line is for intercooling plus regeneration. Okay. In one case intercooling is added to regeneration, in another case reheat is added to regeneration. So, intercooling has a stronger effect. So, the efficiency is very high at this point, even at such high values of r, where we know that with r the efficiency is decreased for regeneration cycles. Still we have efficiency which is very near to 70%, around 69%. Okay. In our case t was not equal to 6, t was equal to 5. So, that would correspond to this dashed line, red dashed line, and r equal to 10. So, this is around 67-68%, that is what we had obtained. This is slightly higher compared to the corresponding blue line. Okay. So, always this is slightly higher, there is a small gap with the corresponding case for reheating, okay, although both are very favorable in terms of efficiency. And finally, when we had combined all three together, we get very high efficiency as we had noted, and the efficiency decreases also very slowly. Okay. So, for example, at t equal to 6, the efficiency at t equal to 6 for r equal to 10, this is very high, around 77%, 78%, but even if we go to very high r value, still the efficiency remains high, still here it is more than 72-73%, even at a very high value of r equal to 30. So, which is very remarkable that this is almost flat. So, if we use this system, okay, for our gas turbine design, then we can have a very flat performance curve. So, which means that we can take any suitable value of R such that we get the highest work output from the cycle. Okay. So, because the efficiency remains almost similar, efficiency curve is almost flat. So, our case was t equal to 5. So, this blue dashed line, which was still considerably beyond 70%. So, 72, 73%, something like this. So, we had obtained 72%, very high value, and you can see that corresponding to the. So, let us say that red dashed line, which is the second highest case, there is a significant jump of at least 4-5% when we go to the combined cycle. Okay. Even the t equal to 5 line is also higher, and you can see that it decays slowly or at a slower rate as compared to the cases of either intercooling plus regeneration or reheat plus regeneration. Okay. So, this is a very complex map which could have simplified this with having less number of temperature ratios. So, for example, if we had just taken t equal to 5, we would have a very simple structure and you can understand better. I suggest that you draw similar plots. It is very easy to draw. We have already derived the expressions. You have to just use those expressions, and for different values of those parameters, you can plot through any software or any programming tool, and you will can generate curves like this, and that will help you in understanding the problems in a significantly better way. So, you will understand at a much more fundamental level, okay, much more interesting concepts will be clear. So, we will finish this part by having a similar discussion, but quicker discussion on the W net, okay, work versus. So, this is W net. So, net specific work output, okay, or more accurately let us write W net by CPT1. It is written here. So, that is the case W net by CPT1 versus R. So, just to simplify this, because the previous diagram was very complex, I have shown first the cases where there is no intercooling. Okay. So, we know that, let us say that we have simple Brayton cycle which corresponds to this black line, t equal to 2, t equal to 3, t equal to 4, okay, simple Brayton cycle, t equal to 5. So, simple Brayton we know that, or simple gas turbine, or on any other case also we know that the work output increases up to a certain extent and then it keeps on decreasing. Okay, we have discussed this. So, it increases and then keeps on decreasing, and this peak value also we had obtained what is the location at which we get the maximum work output. If you remember, in one of the beginning classes we had discussed and derived the condition for the maximum work output. So, this peak value also gets shifted, the R optimum R value gets shifted for higher values of t. Okay. So, like this. So, t equal to 2 is very impractical, but let us say for a more realistic case t equal to 5, we get something like this, and for our case R was equal to 10 and with R equal to 10. So, here actually I have not, to simplify this, I have not plotted. So, I wrongly mentioned, I have not plotted the non-dimensional values, I have plotted the dimensional values. Of course, we can also plot the non-dimensional values. Okay, I have plotted the dimensional values so that we can directly compare with our results that we had obtained. Okay. So, if you see this R equal to 10, t equal to 5, this was our result. So, it seems it is somewhere around 440 to 450 range, and we hope that that is the case. So, that is the case we see 446. Okay. So, these maps also can be directly used to obtain the work output without solving the entire means or doing the entire calculation. Okay. So, if say we are interested in R equal to 20 for t equal to 5, directly we can see from here that it will be almost similar, maybe slightly higher, 45 point or 46%. Okay. We can more accurately get by interpolation. So, now by adding reheat we know that significant increase occurs. So, t equal to 5, you can see that from here to here we have a substantial jump in the work output, and these gaps keep on, this gap keeps on increasing at higher value, say for example, at R equal to 30. this difference is dramatically higher, okay, and this is for the case with reheating. So, without reheating means both the simple Brayton cycle as well as the regeneration plus simple Brayton, and with reheating means with reheating of simple Brayton cycle and reheating plus regeneration, okay, because with regeneration does not change the work output. So, in our case we were somewhere around here. So, we can see that it is quite high, around 560, 570, and that should be the case which we had obtained. So, 564, okay, and these values also can be verified, okay, and this difference would have been higher if you do a calculation for r equal to 30, you will see that you will get a major shift in the value of the work output. Now, when we add intercooling to this, the plot becomes more complex, but just take one value, say T equal to 5, okay. T equal to 5, this solid black line is for simple Brayton cycle and regeneration cycle, okay, T equal to 5, this is for T equal to 6. Then this blue line, okay, this is when intercooling is added. So, regeneration reheat plus intercooling. So, this is the T equal to 5, you can see how much higher this is, because combined reheating and intercooling gives a much higher value. Pure intercooling also increases the efficiency, but not to the same extent. So, pure intercooling, these black dot lines are for pure intercooling. So, this is for T equal to 5, this is not, this is still higher than the corresponding simple Brayton cycle, but not as high as the solid blue line which is for reheating. But combining these two gives us the maximum work output, and we get the maximum work output, as you can see, can get very large work output. Here I have plotted in non-dimensional form, okay, because that is the way it should be compared. You can of course plot in dimensional form also, okay, because or directly non-dimensional is our results and compare here. Okay. So, you get an example of both types of plots, both nature will be exactly same, only the values are different. So, we get a very high value in non-dimensional form. You can see that for T equal to 5, the lowest value that we had obtained, which was for simple Brayton, in non-dimensional it is slightly below 1.5, and the best condition it is more than twice, it is just below 3.5. Okay. So, we have increased the work output to a considerable value in non-dimensional term. This is for T equal to 6, for T equal to 5, which was our case. The increase of course is not as high, but still it is much higher, it is still beyond 2.5. So, more than 60% increase has occurred in this case, okay, 60 to 70% increase, and that is what we had found. So, with this we finish this part, okay, all the ideal cycles, and then we go to more practical cycles or more realistic gas turbines, okay, which are based on these concepts. So, these concepts are very important still, but the calculations will now incorporate the effects of losses, then other variations like fuel, addition of fuel, changes in Cp and changes in gamma, all these things we will consider in the next week. Okay. So, in this class we have learned the concept of design point calculation and generation of performance maps, and then we have seen actual performance maps which we have drawn by plotting our derived expressions or by doing repetitive design point calculations, and then we have compared all the cases, and we have seen that our conclusions when we have discussed each of the gas turbines during the classes are directly apparent from the performance maps also. So, these are the references. So, with this we end today's class and week 3 of this course. Thank you, and we will meet again in the next class. Thank you.